What's up, guys? This is weird. Oh, that was awkward. Welcome to this very first version of like a shooting here in this empty classroom. This was supposed to be mine, by the way. So welcome to the best classroom and the best advisor of the best section of all time, the most quiet one. So in this video, since this is the end of second term, I thought it would be funny to do something like this. I don't know if it's recording already and my voice is also echoing. So what we're going to discuss here is, it's going to be about polynomial functions, its graph, pene, pono. Is that right? Yeah, pene, pono, yeah. And word problems. Jump right into it, bro. And here, as you can see, the presentation is homage to f of x. You should go listen to Four Walls by them. It's really good. Same with When I'm Alone. It's a really good K-pop group, but it's a bit dated compared to the new ones, but I think they're third generation or second. But anyway, so speaking of f of x, we're going to talk about polynomial functions once again. And what you can see here on your screens is about the general form of these equations. So as you can see here, the function has that kind of given, and you're like, sir, what does a sub n, x raised to n mean, and so on. As you can notice here, the exponents decreases. It implies that you have here the terms are arranged properly from the highest degree to the lowest. So that's basically it. But here you have to pay attention also that your coefficients are real numbers, and that a should not be equal to 0. Because if a is equal to 0, that will make that specific term or those terms non-existent. And of course, n should be non-negative, because if the exponent is negative, it will make the given term no longer like that. It's going to flip, and that's going to make it wrong. Okay, so in this case, we have here for polynomial functions, it's important to take note that the domain is the set of real numbers given f of x is equal to a times x raised to n. And if n is odd, the range is the set of all real numbers, and the graph is symmetric over the origin. So these are the basic concepts about polynomial functions that were discussed already in line with the graph. So quadratic, linear, but this time around we're focusing more on quadratic and above. So in this case, polynomial functions can look like this. So as you can notice in your screens, you have there 6 examples. If the degree is 0, that's a constant function. That's why, as you can see, it's a horizontal line. Now, if the degree is 1, that's going to give us a linear function. That's what you guys discussed back in grade 8. While quadratic equation or function is for degree 2. That's what you discussed in grade 9. And from degree 3 onwards, that is the ones that we're going to try to explain to you in terms of polynomial functions. So for example here, we have the polynomial functions g of x, which is equal to x squared. As you can see, the graph of it is a parabola. While for h of x is equal to 3x raised to 4. And as you can notice, it's not necessarily a parabola, but it's close to it. And again, this is raised to 4. This is a quartic function. And as you can notice earlier, it's telling us it should look like something like a W or something. But there's a reason why the graph looks like that. That's something that we're going to mention later. But the most important part here that we have to take note of is that the leading coefficient for both examples are positive, and the exponents are both even. X squared, x raised to 4, even exponent. 1x squared, so positive. 3x raised to 4, so positive. So take note of that. Positive leading coefficient with an even exponent. So those are their graphs. But how about if you make those things negative? So what will happen now is that we have the negative leading coefficient with an even exponent. It will flip the graph. So you can notice it's now going downwards. Okay, that happens when the leading coefficient is negative and the exponent is even. While the next example is, how about if we have polynomial functions where the coefficients are still positive, the leading coefficients, but now the exponent is odd. So you can notice this is an example of a cubic function and a quintic function. Okay, as you can notice again, sir, why is it not the same as the one that you showed earlier? There's a reason behind that. What makes a graph looks like the one at the right? But the one thing that I want to emphasize here first is that their leading coefficients are both positive and their exponents are both odd. So their image looks like that. Next is if we have polynomial functions where we have negative leading coefficient, as you can notice, negative x cubed. Then the one on the right is negative 2x raised to 5. So their exponents are also odd. And basically, it's similar to the one that was previously given, but this time around, it's flipped. And that's the effect of having a negative leading coefficient. Now, you might be wondering, sir, why are we not focusing on the specific parts, because the thing that we're going to discuss here in the beginning is to understand and somewhat describe the graphs of polynomial functions more about their end behavior, meaning to say what's the direction that those two end parts of it leading, like where will they extend infinitely. So as you can notice earlier with the first example, the direction is that both sides are going upwards, the left arrowhead and the right arrowhead. And while for the second example here, they're both going downwards, while for the third one, it goes from down to up. And then the last one is from up to down. So you can see the differences with their end behaviors and the direction that they're heading into. So in this case, we can have here what we call as like a abbreviation of the concept. We have here pe, ne, po, no. So as you can see here, it's actually Garfield. I don't know if he makes sense here, but yeah, I use his face. Um, I think I can show a picture of him while trying to do this image. I was hoping to use his actual body, but he got mad at me while doing this one. Don't worry, no animals were harmed in the making of this image. But anyway, so the meaning of PE is positive even, NE means negative even, PO means positive odd, and NO means negative odd. So in this case, for polynomial functions, we can say that we have the following. The sign of the leading coefficient is positive, the degree is even, the sign is, basically the left and the right arrow are both going up. If it's NE, negative even, both are going down. If it's positive odd, it's going to be down up, negative odd, that's up down. So what you're seeing on your screens right now is the interpretation of pene pono in terms of a table, or if you want to, you can visualize it more with a graph. This is what pene pono looks like. When you have, for example, x squared, negative x squared, x cubed, and negative x cubed. Again, what we're focusing here is the end behavior of a polynomial function. To continue, let's go to the most important part of this discussion, which is about the intercepts. So we're going to focus on the x-intercepts to be in particular, and basically this one is what we can relate to from our previous concept, which is the rational root theorem, remainder, and factor theorem. So basically, the x-intercepts in the context of the Cartesian coordinate plane, these are the points on the graph that you can see that passes through or is on the x-axis. That's why it's called intercepts. That's the part where your graph, your drawing, passes through the x-intercepts. And at the same time, not only are they called x-intercepts, they are what we call as the zeros of the functions, or again, in the context of our previous lesson, we call them as our roots. So they're all connected. So let's say we have here this example, graph the following functions and identify their intercepts. So I want you to understand here that you can use your calculators and maximize them in order for you to graph a function like this one that you're seeing. The purpose of that is for you to, again, realize that these things right here are not that complicated to graph. So you can have different techniques on how to start with this one. You may start by thinking, is this falling under pe, ne, po, or no? So as you can notice here in this example, it's x raised to 3. It's positive and it's odd. So that falls under po. So our expectation is our graph should look like this. That is our expectation. So in order for you to draw a graph that looks like po, or positive odd, you should first get the intercepts. Now, to explain this to you guys without wasting so much of your time, if you still don't know how to get the x-intercepts, you may refer to the previous video, which is the rational root theorem. Or if you understood the concept already, you may maximize your calculators by typing in the values for the numerical coefficient. For example, here, x cubed minus 2x squared minus x plus 2, you should type in, take note, you should type in the following: 1, negative 2, negative 1, and positive 2. If you type those things in your calculator under the equation part, you will be able to get its x-intercepts. Okay, so that's how it works. So you may do that for the meantime, and then you try to figure out, what should be the x-intercepts of this given example. So that's what you have to try and figure out. I'll give you guys 10 seconds. Sorry, I'm searching for the answers. It's here actually. So the intercepts that we will get here are negative 1, 1, and 2. I'll write it here. So you're going to get x is equal to negative 1, 1, and 2. These are your x-intercepts. Those are the values of your x. So what's the importance of that to our answer? Not only were we able to get the x-intercepts, we can now actually graph it. Now, to give context to this one, again, the first example will be the long version as always. So for you to understand this x is equal to negative 1 simply implies that you can find a point at negative 1, 0. While for 1, that implies that there is a point at 1, 0. As for 2, that implies there is a point at 2, 0. So what you're going to do now is you're going to plot those points in the Cartesian coordinate plane. So you have negative 1, 0 here, negative 1. Again, guys, this is the x-axis. So the x-intercept should be found there. You have here 1, 0, and then lastly you have 2, 0. So again, once you've graphed it, you will now be able to, once you plotted the points based on the x-intercepts, you will now be able to graph the pene-pono kind of thing. So since this falls under SPO, so you can draw something like this, and it passes through this one. There will be a turning point here, another turning point here, and that's it. So this is the graph of the given polynomial function. You might be asking me the question, sir, how do you get these turning points in this example? Actually, it's not an exact turning point. There is a way to get it, which you can research on if you want to. Basically, it involves the concept of calculus. So as in the meantime, once again, as I mentioned earlier, our focus is not mainly the turning points, but more on the end behaviors. Because again, you're still in grade 10, so we have to take it easy. Now, what can we actually do with the x-intercepts other than graphing and plotting points? These intercepts can be used in order for us to get the factored form of a polynomial function. Sometimes, when you get the x-intercepts, it's just a one-step kind of thing, but sometimes there's something that you have to add. But in this example, it's basically like this. So if you have negative 1, so x is equal to negative 1, x is equal to 1, x is equal to 2, x is equal to negative 1 is the same as having or saying that you have x plus 1 as a factor. While if you have x is equal to 1, you can say that you have x minus 1 as a factor. And if you have x is equal to 2, you can say that you have x minus 2 as a factor. Because the concept that we're doing here is somewhat the backwards way of doing things. So if you want to understand this better, if you have, let's say, x plus 1, and you equate that to 0, what do you do here? You may isolate the variable, you transpose, or you subtract 1 to both sides, you'll get x is equal to negative 1. That's why when you get the x-intercepts and want to identify the factored forms of that, the factored version of it, basically you will simply change the sign and combine it with x. But again, sometimes there are extra steps that we need to do. You may want to check it if you want to, like this one is x minus 1 equal to 0, it's x is equal to 1, this is x minus 2, so x minus 2 equal to 0, x is equal to 2. So all of them are correct. So meaning to say the factored form is x plus 1, that quantity times quantity x minus 1 times quantity x minus 2. So this is your factored form. That will be an important concept, especially when we work on word problems. So you can see this is the graph, and those are the intercepts and the factored form of the given polynomial. Okay, so since it's the first example, I have to somewhat take that slow and make you understand how it happened. Now, for the sake of the other examples, you may pause some parts of it, so you may try using your calculator, or if you want to again, you may do it manually with maximizing the concept of the rational root theorem. So let's say we have the example x raised to 5 minus 1. This one right here is expected to be a quintic function because it's raised to 5. So it's not expected. It is a quintic function. And since it's raised to 5, it's odd. And since it's positive, it's PO, or positive odd. So your expected graph is similar to the first one. So if you identify the intercepts of this one, it will only give you the following: x minus 1 as one of your factors, meaning your x-intercept is 1. And you will have another factor, which will be x raised to 4 plus x raised to 3 plus x squared plus x plus 1. Here, it might be a long example, might be a bit complicated, but the purpose of showing this is for you to understand, if you look at the graph on the left, it only passes through, or passes through, the x-axis once. So basically, what I want you to understand here is this: if the polynomial is odd degree, there's a chance that there is at least one or more solution or roots or intercept. That's the concept that I want you to understand from this example. Again, not because it's raised to 5, you're going to automatically have 5 roots. Sometimes you can have 1, 2, 3, and so on. So now let's try another example. What if we have x raised to 4 plus 2x cubed minus x minus 2? So again, let me try to think of ways how to get the roots of this example. Let me pause in this part. And in here, what you will see is that it actually has roots. And the roots of it is basically negative 2 and 1. As you can notice with its graph, it doesn't look like a parabola anymore, because again, the expected look for a quartic function is like a W. But again, there's a reason why the turning points look like that from time to time. We will have more examples. You can notice we have 2 intercepts, even though it's raised to 4. But I want you to look at this example right here. So we have s of x is equal to 3 times the quantity x minus 2 raised to 2 plus 5. Now, if you remember your grade 9 days, if you try to graph this one, it will give you a parabola. But because of the plus 5, it will have a huge effect with where the graph will go, meaning it will be shifted somewhere else. So what happens here is that your parabola, without the plus 5, it will still be on the x-axis. But because of the plus 5, look where it went. It went up. The emphasis is that the plus 5 affected it in a way that it went from here to here. That's one of the things that you guys have discussed back in grade 9, which is the shifting of the graph. If you haven't done that, maybe in the future you will. That's the concept that I wanted to understand. So earlier, we were talking about odd degree polynomials, and all of them has at least one x-intercept. But since now this is even, that's like this example, there is a chance that there might be no x-intercept at all. So if earlier for odd polynomials, you have at least one forwards, while for even, you can simply have none onwards. So that's the concept that I want you to understand there. Okay? Basically, what we're talking about here in the meantime is about how the graph looks like, what is the importance of their degrees, and its effect to how the graph will look like exactly. So in this case, let's try some more examples. Let's say we have here t of x is equal to x cubed minus 3x plus 2. So if you use your calculator here again, you will be able to get the following intercepts. X sub 1 is equal to -2, and x sub 2 is equal to 1. So you might be thinking, oh sir, basically just like you mentioned earlier, since this is an odd degree polynomial, we're good with 2, right? Actually, that's the thing that you have to be careful with. You have to double check whether there's actually just 2 roots, or maybe the other one is hiding. Maybe there is a multiplicity. So again, this will help us go back to our previous lesson. We would need to check how to get the other one, or if there is another one, by doing continuous synthetic division, or you may do factoring, or you may even do quadratic formula. In the meantime, let's proceed. So we'll have, for example, -2. You have +1 from x cubed. You don't have an x squared, so 0. Then you have -3, then +2. So put the line here, bring down 1. 1 times -2 is -2. 0 minus 2 is -2. -2 times -2 is 4. -3 plus 4 is 1. 1 times -2 is -2. This will be 0. And once again, this part, I think you can factor this already if you want to. Again, if you want to. We'll show that later. But now if you want to continue, let's use 1 now instead. So you'll have here 1 times 1, 1, -2 plus 1, -1, -1 times 1, -1, we get here a 0. So what's the meaning of 1, -1, 0? Always remember, the last term is also a remainder, followed by the constant, and then the x. So this one will become x minus 1 equal to 0. Since you have that kind of situation, you can isolate the x variable. So you're going to have x is equal to 1. As you can notice, your roots are -2, 1, and another 1. So there is indeed a multiplicity of 2. So still you have actually 3 values for x. In a sense, there's 3 roots, but 1 is a multiplicity. And that has an implication with the graph. So this one has 1 multiplicity of 2. But before we head to the graphing, I want to show this part. If you want to do factoring, this one is, what is this? X squared minus 2x plus 1 equal to 0. This is a perfect square trinomial. The factors are x minus 1, x minus 1. So x minus 1, x minus 1. This is +1, this is +1. Okay, my bad. So to continue, this is x minus 1 and another x minus 1 here. Or if you want to, again, since there's a multiplicity of 2, you can write it as the quantity x plus 2 times the quantity x minus 1 raised to 2. Now, this is an important part for you to understand. When you graph this, you can have a point at -2 and another at 1. Again, you cannot have 2 points on one location. Basically, it's the same point. And what will that imply? This still falls under PO, so it should look like this. And if you graph it, pay attention, have here -2, this is 1, and this is your graph. And you might be asking, sir, what happened with this graph? Basically, since there is a multiplicity, instead of passing through the x-axis, it will bounce off. That's the effect of the multiplicity if it is 2. Again, if the multiplicity of 2 is the one you can observe in this example or any examples, there will be a bounce that will happen. And the bounce happens at the point where the multiplicity exists. Since my multiplicity is a 1, the bouncing will happen on 1 or at 1. Which one's correct? 1 or at? I don't know, man, but yeah. Grammar is not my strong suit. But anyway, let's proceed with another example. Again, this is how it looks like. Again, it bounces at positive 1. So if we can continue, we'll see here this function x raised to 3 plus 5x squared plus 8x plus 4. Once again, you may type this entire thing, and then, or you want to do it manually, you'll get the entire x-intercepts for this function. So what you will get here are the following. I think there's a multiplicity here again. So you have x is equal to negative 1 and x is equal to negative 2. So we know that our factors are as follow. We have x plus 1 and x plus 2. So we want to look for the other one. So in order to do that, let's try continuous synthetic. I'll use negative 1 first. So you'll have 1 times negative 1, 5 minus 1, 4. 4 times negative 1, negative 4. 8 minus 4, 4. 4 times negative 1, negative 4. This will be 0. Let's now try to use negative 2. And again, that can be factored if you want to. You'll have 1 times negative 2, positive 2, negative 4, 0. So this means you'll have x plus 2 equal to 0, or x is equal to negative 2. And as you can notice again, there is a repetition of negative 2. That implies that there is a multiplicity. There's a multiplicity for negative 2. So that's what we need to take note of in this example. So now we will graph these things on the Cartesian coordinate plane. So you're going to have here your negative 2, is negative 1. So what will happen is that, as you can see, there is a repetition or multiplicity at negative 2. So hence, your graph will look like this. What can you notice from this graph compared to the first one? Basically, there is only 2 points indicated because, again, it's a multiplicity similar to the previous example. And here is one of the most important part. Again, it bounces off because there is a multiplicity of 2. Again, it bounces off because there is a multiplicity of 2. Now let's try to talk about the last two concepts I want you to understand in terms of a graph of a polynomial function. Let's say we have x raised to 3, sorry, not this one, x plus 2, that quantity, raised to 3. Now, what will happen to your graph here? Actually, this kind of example is something that you don't have to overthink on because it's not that hard, you know? Now I'm yawning. Dude, it's it's like 10 o'clock in the morning. No, it's almost 11. I'm so sorry. I barely had any sleep. And I have to record this in a room that echoes. So anyway, so this one right here can also be rewritten as x plus 2, your first quantity. Your second quantity is also x plus 2. And the third one is also x plus 2. Hence the 3 for the exponent. It's not hard. So that means that if you equate these things into 0, they're all going to give you one answer, and that is negative 2. So meaning there is a multiplicity of what? Multiplicity of 3. So the multiplicity divides with the, so basically, how do I say it right? The multiplicity basically comes from the exponent of the given binomial. Again, this is not for all cases. If you remember our previous example earlier, there's a grouping symbol also, but it doesn't fit the bill. So you still have to check, double check if it works or not. So in this case, we know that there is a point at negative 2 where there is 3 I almost said municipality. I hate my students. They say that all the time. So that means that when you graph this one, this is still falling under positive other pole. Your graph should look like this. Or more forward, you may do a more forward example of this one. But the most important part is we want to see you at this certain part have a longer kind of life. In this case of multiplicity, you're gonna have to stay a bit in there in this part of the graph because there's a multiplicity in that. It's basically like if you wanted to jump off, but somebody told you no and stopped you, and then another one told you the same thing. So it's basically how polynomial functions when there is a multiplicity of 3 goes. So this is how it looks like. Again, as you can see here, I'll zoom in a little. It's not just a point that's being crossed by the graph. It's crossing some points around that value. So there's a reason behind that. And that is the multiplicity. So what if now we have a multiplicity of 4? What will that imply? Basically, it's the same concept since this is inside already of a grouping symbol. So this will give you x plus 3 multiplicity of 4. So that's how it works. And again, you're going to have a point at 1, 2, 1, 2, 3. So there's a point here. And again, this falls under positive even. So it should be a letter V of sorts. So from there, it will look like this. It doesn't look much like a square. Sorry, it has to be next. Doesn't have to be necessarily like a whatever kind of thing, but the point is here is that it has a multiplicity of 4. So that's why this part right here should be thicker, should be longer compared to the previous examples, because it's going to stay there. So just to visualize it, it looks like this. That's the face, that's the body. So you have to have this section. It's important that you get this section correctly. There is no enhancement for this one. You just have to really just dive into it, understand it better, ask questions, and you will be able to master it. Now, let's say that we have the given polynomial function that we had earlier. P of x is equal to x cubed minus 2x squared minus x plus 2. Now, we have already identified that the zeros or the roots of this is the x-intercepts, negative 1, 1, and 2. The factored form is x plus 1, that's your first factor. Second one is x minus 1, and the last factor is x minus 2. So I want you all to understand in this part, not necessarily a thing that I want you to dwell on, but something that you have to understand. Now, these polynomial functions can be better understood with the help of 4 regions. In this case, there are 4 regions, but not all the time will you have 4. The number of regions depend on the number of x-intercepts that you have. As you can see, there are 4 intervals here. You have the first interval as negative infinity to negative 1. That is because it's all the things on the left until it reaches your first x-intercept, which is negative 1. And then your next interval is from your first intercept to the second one. So it's negative 1 to 1. And then your third is from 1 to your third intercept, which is 2. So basically, the regions are negative infinity to your first intercept, your intercepts, and then the last one onwards to positive infinity. I hope that one is better understood that way, with that way of explanation. And then you might be asking, sir, what's the relative and the relative maximum and relative minimum point for? Those are the points where the turning points happen, right? Now, you might be asking, why are they called relative and not just maximum or minimum? Remember that your graph here extends infinitely, and we will never be able to identify the maximum or minimum points. The reason why the first one here that you're seeing is maximum, it's in the context of it being above the x-axis. While for minimum, of course, that's lower. So that is below the x-axis. Now, what I want you all to understand here, the purpose of these regions is for you to also better understand how these things work. Now, what these regions are for and why the graph looks like that. Why is the graph here, there, above, below? So to better understand that, let's have this table for the intervals. And as you may notice, sir, what those signs mean? How do we identify them? So to better understand this, let's have example number 1 for your first interval, which is x less than -1. So think of a number that is less than -1. What we can think of, for example, is -2. So let's use -2 for this example. So if you have x plus 1 as your first factor, you will simply substitute -2. So -2 plus 1. The answer there is -1. That is still negative, hence the negative sign. Now if you have x minus 1, let's have -2 minus 1. That is -3. So still negative. Now if you have x minus 2, that is -2 minus 2. That's -4. Still negative. So to get the answer there, right, when you have factors, you multiply them to each other. So negative times negative is positive times another negative, that will make it negative. Hence, your p of x is negative for the first region, for your first interval. That's why it is below. And if you notice, for your first part, this one is below the x-axis. That's why I have to emphasize that. If you continue this process, you may substitute something that is in between -1 and 1. The easiest number there is 0. So x plus 1, 0 plus 1 is 1. 0 minus 1 is -1. 0 minus 2 is -2. So a positive times a negative, that will make it negative. Negative times negative is a positive. Hence, this is the part of the graph that should be above the x-axis, the second region. And as you can notice here, it's region number 2, it's on top. Okay, that part of our graph, the way that it looks like, it goes up. It's above the x-axis. Similarly, if you continue with this one, you have 1 and 2 as your endpoints, and you're supposed to think of a number between that. You may think of using 1.5. 1.5 plus 1 is 2.5. 1.5 minus 1 is 0.5. But 1.5 minus 2 is -0.5. Positive times positive, positive times negative, negative. Hence, it's below. And as expected, the graph is below the x-axis. And if you continue with that one right here, the last one, x is greater than 2, we can have like 3, for example. So you have 3 plus 1, that will give you 4. 3 minus 1, that will give you 2. 3 minus 2, that will give you 1. So all positive. So it's definitely above. So this table right here, the regions and the intervals you were able to form thanks to all those regions, again, is the position of your curve relative to the x-axis. And just again, a disclaimer, not all the time will it be 4 regions, not all the time will it be alternate. You really have to substitute to identify it. So to save much time here, you can have this example, let's say, not this one anymore. Let's say that we have this example right here, where you have the function wherein there is a multiplicity. So when there is a multiplicity, that's when the number of regions decrease a little. And as you can see here, we only have 3 regions because there is a multiplicity at -2. Sorry. Positive 2. There's a multiplicity there. Wait. No. Why am I saying the wrong number? Multiplicity at +1. Oh God. I'm so sorry. I made 2 mistakes there. So since there's a multiplicity there, as you can notice, it bounced. Then in that case also, as you can notice, there are only 3 regions. And you will have a table like this when you substitute. You can notice below, above, above. Because it didn't go down when there is a multiplicity. There is a bounce that happened. That's why it's above, above. Okay? So I want you to understand with that one long part that we discussed, that basically you will form regions based off of the negative infinity to your closest intercept, then the intercepts, and then after that, your last intercept forward to positive infinity. And then you will be able to form these intervals, and all you have to do is to give out a value for x that satisfies it. Like again, if it's lower than -2, it could be -3, -4, and so on. It will still have the same concept, because what we want to get here is not necessarily the answer, but the sign of the answer. And then from there, we multiply them and to check if it is indeed correct where you will see the curves. So basically, this long part is an explanation mathematically of Penepono. At the same time, how it will look like, the positioning, and so on and so forth. Okay, so once again, the polynomial functions looks like this, and that's their regular look. That's what I want you to understand. Okay, so I hope that one is understandable. Now let us talk about word problems involving polynomial functions. This is going to be fun. This is going to be a bit long, but I will try my best to explain every little bit of it so that you will understand the parts that you can skip, parts that you can shortcut, parts that you can really work on yourselves so that you will know how word problems work. So our first word problem is here. It states that we have Carl and he decides to use a 30 centimeter by 24 centimeter cardboard to make a box where he can store his accessories for his gadgets. By cutting out the squares of the same size from each corner and bending the sides up, he wants to form a box that can occupy a space of 1,400 cubic centimeters. How large a square should be cut from each corner? So for this to be better understood, we would need to draw a rectangle. I'm going to need the help of this one right here. So to save time, I will draw two rectangles immediately. This is my first rectangle here. The other one will look different. So, oops. Okay, anyway. So your first rectangle should look like this, right? It's basically a two-dimensional figure, the cardboard box, based on the context of it all. And here it goes. So as stated in the word problem, you have here it's 30 centimeters by 24 centimeters. Hence, this is your length, and this one is your width. So our length is equal to 30, and our width is equal to 24. Then the next step is that he wants to cut out some squares on the sides. So basically, he wants to cut out these pieces here, equal squares. So why is this person cutting those parts of the squares? Sorry, the part of the rectangle, those squares. Why? Because the purpose of it is that Carl wants to fold it up so that he can form a box using it. This is a side story while I'm drawing on this one. Back in my day, when I was your age, I used to create boxes out of cardboard box or a cardboard or like old ones. Like I used to recycle these things, and I fill it up with things that what my crushes like back in high school, and I give it to them. They appreciate, handcrafted things, and you may do that if you want to. You may do it while you're listening to this one. So basically, cut up the squares on the side and you may start folding. But here's the dilemma. Since this is a word problem, there is no actual measurement here. And that's what we're trying to figure out. What will be the measurement of that? So from a two-dimensional figure like the one you're seeing on the left, we're now going to have a three-dimensional figure. And how will it look like? And what does it imply? Basically, you're now going to fold this figure up. So what will happen is that it will no longer be just a rectangle. It will now become a rectangular prism. So it can look like this. I'm sorry, my drawing is not that straight anymore, but basically that's how it will look like. I'll just put in what you cannot see, which is the fact that it's a rectangular prism. Now, basically this happened because you folded it up, and there is something I want you to understand here. Simple question. You'll better understand this if you did it while I was yapping a lot. If you try to do this on your own, you will understand that the length is no longer the same measurement as it was before. Same case with the width, because you folded two parts for each measurements. So for length, it has been folded or subtracted with two folds. Same case with width. So since we're looking for this thing, and as you can notice, this is now three-dimensional. Other than length and width, it now has a height. And since we don't have a value for height, we will give it x. Height is x. In this context, since you folded each dimension twice, two folds. So basically, your length from originally being 30 should be subtracted with two folds or 2x. And for the width, it will be the same thing. Sorry, it will be 24 minus 2x. And these are your representations. So from having a two-dimensional cardboard box, you now have a three-dimensional cardboard box. Thanks for folding, you now have a height. Okay? It's better understood if you did it while I was yapping. Now, let's use these representations in order for us to actually get the values. So once again, your height is x, your length is 30 minus 2x, and your width is 24 minus 2x. And now what we're going to do is to maximize the formula for volume. So the volume is equal to length times width times height. This one is for the volume of a rectangular prism. So here, to save time, you can make a function here, which is volume of x in terms of x, wherein your length natin guys, ayan ha, 30 minus 2x. So sulat natin yan, 30 minus 2x. Substitute lang. Next, your width is 24 minus 2x. And then lastly, you will have your height, which is x. You'll simply substitute all those things here. You now have your volume function. Now, you can maximize your time here if you want to, but again, since it's a first example, let's slow down a little. So what you will do first is, if I were you, I'll distribute x to the one next to it. So let's just copy 30 minus 2x for the meantime. Then distribute x to 24 minus 2x. X times 24, 24x. X times negative 2x, you will get negative 2x squared. Now you have two binomials, so what you can do with this function is that you're going to apply the concept of distributive property or FOIL method. So you can multiply 30 times 24x, that will give you 720x. Then you may multiply the outer terms, 30 and negative 2x squared, that's going to give you negative 60x squared. Multiply the inner terms, negative 2x times 24x. It's going to give you negative 48x squared. And lastly, you may multiply negative 2x to negative 2x squared, and you will get positive 4x cubed. So here, what you will do now is you will rearrange the function. If you remember earlier right, with the introduction, it should be arranged properly from the highest degree to the lowest. So the volume of this function, the volume function, or whatever you call it, will have 4x cubed, and then we will simplify negative 60x squared and negative 48x squared. They are like terms. Negative 60 minus 48, that will give us negative 108x squared. Then plus 720x. Now you might be thinking, sir, what do we do now? Since we are given with a value for volume, which is 1,400 centimeters cubed, you may substitute that to our function. So this will become 1,400 is equal to 4x cubed minus 108x squared plus 720x. So what you have to do now is you will simply transpose 1400. So from our function, we're now going to have an equation, which is 4x cubed minus 108x squared plus 720x minus 1400 equal to 0. And once again, to explain this to you guys, what we did with 1,4 is that we transposed it to the other side. As you can notice, it's a long process. So you start with representation, then you substitute that to the formula, then you multiply, and then you arrange, you combine like terms, and from there, you may maximize the use of your calculator and do what we did earlier in the graphing, wherein you will identify the x-intercepts. Okay? So this is an important part of the discussion. This took a little. Okay. So in this case, if you identify the x-intercepts of this one, you're gonna get values like x is equal to, I think it's like 3.8 something or 3.9. You're gonna have x is equal to 18.1 something, and then the last one is x is equal to 5. So you have here three different values, and in this case, you have to work on the word problem in a manner that you remember that this is a real life word problem. It should answer it properly, the context of it. So among the three values of the x-intercepts that you can get using your calculator, these two things are approximations. And if realistically speaking, you cannot make those kinds of measurements on your own. The most realistic answer here is 5. So that's the one that we're going to use. Meaning, substitute that. Your height is x, so meaning height is 5. Since your length is 30 minus 2x, this is 30 minus 2 times 5. That's 30 minus 10, you will get 20. While for the width, it's 24 minus 2 times 5, you will get 14. And as you can notice, if your length, width, and height is 20, 14, 15, volume is equal to 20 times 14 times 5. This one will give you 1,400 centimeters cubic centimeters. So it's correct. Now, for you to understand this in the context of graphing, if you graph this entire thing, you will notice that the graph will pass through 3 points. You have there the 3 point something, 5, and the 18 point something. That's why we're going to use 5. Okay? Again, it depends on the context of a word problem. Sometimes there's a chance if even you did the right thing, you got the x-intercepts, but in the context of the word problem, none of them will work. That's why you have to answer the questions carefully. So now, how large a square should be cut from each corner? So we'll say 5 centimeters by 5 centimeters. That's the measurement of that square. Because the height is 5 centimeters and it's a square, all sides are equal. So it's 5 by 5. Okay? So to visualize that, the squares earlier, this should be 5 by 5. That's the one that you're going to cut off at each side. So that's the answer to the word problem. Once again, you have to answer the word problem correctly. So that's the first one. And it took us 10 minutes to do that. Well, that's the norm though. It's a word problem. You have to take your time there. Now let's have another one. This will be our last one. Yay! So our last word problem is similar. It's going to be a Cariton classroom. A trolley or a cart is twice as long as its width, the length, and its height is 2 decimeters shorter than its width, with a volume that is 1,600 cubic decimeters. Now, for you guys, short trivia, the Cariton classroom is made famous by Ephraim. Anya Florida, am I correct with the last name? I forgot. I'm giving a trivia and I forgot the last name. So basically, he's a Filipino, and you know those trolley that people push in order to move stuff. In the local scene, let's say the local scene, in troubled places in the country, people create these cardboard boxes and put wheels under them in order for them to collect junks, and using that to feed themselves, help them feed themselves, collect junks, move those trolley to help them carry instead of just using sacks. So they do that. So Ephraim had this idea that instead of having junks on the trolleys, the carton, he instead made use of books and some sort of a moving library, and he brings it to those same troubled streets and educates the young. And that's something that's really commendable. But anyway, other than that short story, let's work on this one right here. So we have the following measurements. The length is twice as long as the width, and you have here your height is 2 decimeters shorter than its width. And as you can notice here, among all of the measurements for this given, given, the most mentioned thing is the width. And since it's the most mentioned thing, the one that we're comparing almost everything, actually every single side to, is your width. So what does that imply? Your width is going to be your x. Diba? That's what we do. We compare things to our x all the time. Joke, that's bad. Don't compare your present to your past. Okay, don't do that. Only in math can you do that properly. Okay. Anyways, oh god, why am I still joking? I'm so tired. Anyway, you have here the length is twice as long as its width. So therefore, your width is going to be your length is going to be 2x, since twice. And then for your height, it's 2 decimeters shorter. So your width is x shorter, so x minus 2. So now, since you have that, you're going to use all those three things in order to answer the word problem. So let's work on it again. So you have the length as 2x, width as x, height as x minus 2. Am I correct? Yep. We're still here. So we continue with that one. Same volume is length times width times height. V of x, for example, you have your length as 2x, width as x, height as x minus 2. So we continue with this one. V of x is equal to 2x times x, that is 2x squared. You have here x minus 2. And here's again, you can have shortcuts here. You can substitute 1/6 immediately, your volume, to the function if you want to. Let's do that. Since earlier is the step-by-step process, we can teach you techniques here. Substitute nyo na siya. 1/6 is equal to, multiply, 2x squared times x, 2x raised to 3. 2x squared times negative 2, negative 4x squared. So now you have to transpose 1/6 to the other side. So you're going to have 2x cubed minus 4x squared minus 1,600 is equal to 0. So now you have to work on with your calculators in order to figure out the values that you're going to have here. Be careful here, walang x value. So you have to be careful on how it's going to look like. Okay, I'm gonna try to find the intercepts of this one too. How do I do that? What will be the intercepts of this one? X-intercepts calculator. Wait guys, I'm solving it with you. You may skip this part if you already solved. Man, I forgot how to do this, right? 2x raised to 3 minus 4x raised to 2 minus 1,600 is equal to 0. Yeah, that's correct. That's correct. So we'll try to find the roots of it. And here is the funny thing. That's correct. The roots of this given example is as follows. You have positive 10. You have x is equal to negative 4 plus 8 imaginary. You're also going to have negative 4 minus 8 imaginary. And now I think it's pretty obvious with this kind of example. You cannot have imaginary dimensions. Okay? Maybe in your head you have the Lulu situations, but please don't stay with that. If it's an imaginary situation, it's never going to occupy any space. It's never going to have any volume to it. So just move on. Let it be. Let go. Oh my God. Anyway, corny jokes aside. Now, basically, this is an easy peasy, lemon squeezy. We're only going to use 10 because that's the only number that we can use here for the value of x. So this implies that you have 2 times 10, you have 20, x, so this is 10, x minus 2, so it's 10 minus 2. So this will give you 8. So your dimensions for your volume, your length is 20, you have 10, you have 8. And if you multiply these three things, you will get 1,600 cubic decimeters. So it's correct. Always remember to answer the word problems in terms of its context. And again, those are things that are imaginary. You will not be able to use imaginary measurements in order to create something. Okay? You can imagine something, think of it. Think of it. And your imaginations will not become real unless you do something that is real. Okay? I don't know. That makes sense? So when you graph it, as you can notice here, there's only one actual x-intercept because again, the two are imaginary. So you're not going to see that in the graph. And this one is 10. So that's what I want you to understand. And now, that's the end of this video, supposedly. But there's one thing that I want to discuss first, and this is for further notes. And one of the things that a lot of people may have a hard time in answering or working on. And that's the process of having what they call this, the factored forms based off on the x-intercepts. Okay, I want to explain that. So this is the bonus part, factors of polynomials using x-intercepts. Using x-intercepts. I'm gonna work backwards here, so please forgive me. This will be a goofy discussion, this part. It's your choice if you want to still listen to this one, but this is a bonus part because these are some things that you might see. So let's say we have, for example, when you solve for the x-intercepts, you only got, I was thinking of it, wait lang let me get this one. Let's say I have the following, so example number 1. Let's give 3 examples. Say -1, 2, 3. For example, we have this one. So we have x equal to -1, as discussed earlier. This is the same as x plus 1. This is the same as x minus 2. And this one is the same as x minus 3. Okay. So if you multiply these three things, what is it? Wait. Wala pa yung given, no? Pero may sagot na. Galing ko talaga. Wait lang, guys. X minus 2. You can also have x minus 3. Find the product. Multiply. This one is equal to, if you multiply these three things, this will be x cubed minus 4x squared plus x plus 6. Okay? I want you to take note of that. If you have those roots and you multiply them, the factors, you will lead to x cubed minus 4x squared plus x plus 6. This example will answer the questions that you might have here. But what if, for example, your given is 2x cubed minus 8x squared plus 2x plus 12. What if that is your given? And you may immediately use your calculator here to get the x-intercepts. And you know what? You will get the same 3 x's that I indicated here. These 3 things. You will get x is -1, you will get 2, and you will get 3. Even though you use the same example. You use a different example. Now, the purpose of this one is for you to understand that there is something that is limited in terms of your calculators. Your calculators can give you the x-intercepts, but using that to have the backwards version, so to get the factors, it will be incomplete if you multiply them. Because if you multiply these 3 things, it's just going to give you this, right? So what do you think is the missing number that we need to multiply to get the actual factors of our given here? Diba? Let's say this is x plus 1 pa din, x minus 2, x minus 3. So what do you think is missing in here? Basically, the one that's missing here is the common factor for the given, which is 2. Why is it 2? Because this function right here, if you divide it by 2, 2x cubed minus 8x squared plus 2x plus 12, you divide it by 2, you will get x cubed minus 4x squared plus x plus 6, which is this example right here. So again, I'm explaining here that you can get the factors of a given polynomial with the help of your calculator and the x-intercepts, but not all the time will it lead you back to the original given. You still have to take note, was the given simplifiable? If it's simplifiable, you will have a certain situation like this. Kaya you really have to take note. Not all the time will it be correct, your x-intercepts. So basically, the technology is limited in our time. So you have to still use your critical thinking skills in order for you to get the correct answer. And the last one that I would like to discuss is, what if, sir, I got an answer like this in one of my intercepts. X is equal to 3 halves. How will I do that? Will it be correct if I say that my factor, this is our example number 2, to answer your dilemmas here, will it be x minus 3 halves? The answer is actually sort of correct, but you have to do something. Now, some students will say, oh, sir, can I say x minus 1.5? Unfortunately, no. We don't use decimals when we are factoring, because that will give us different answers. When you try to multiply those things, it's going to give you a different answer. So what do you have to do here? In the context of this one, I'll explain it first in a mathematical way that might be complicated for some, but if you have here, sorry, anong boses guys, x is equal to 3 halves, what you have to do first is you need to multiply both sides by the denominator, which is 2. So if you do that, you're going to have what? 2x is equal to 3. Wow, we're back. Nawala na yung audio guys, sorry. So just want to repeat. If you have 2x is equal to 3, you may transpose 3 to the other side. So you'll get 2x minus 3. So that's your factor. Sir, what if I don't know what to do with that? What else can I do to somewhat double check my work here? Where you have another opportunity to somewhat work with it by, again, cross multiplication, then transpose. If that doesn't work, if your calculators gave you something like this, I'll show this example. What if your calculators instead literally gave you x is equal to 1.5? For example lang, 1.5 talaga yung binigay niya. So your goal here is that you can still do what you did earlier. You can say you have x minus 1.5, but your goal now is to make it whole. So this one, you're still going to refer to the given. Like, is there a common factor in the given polynomial? Just like the one that we did in the first one. So let's say the common factor is 2. So you multiply this by 2 and you will get 2x minus 3. So, sir, I'm still confused. Now, this is my answer and my guide to you. How do you make it like 2x minus 3 and not negative 3 halves or negative 1.5? Always go back to the given. Is that given simplifiable by any number? That will play a huge role, whatever number that is. Okay? So I think that's way too much of me yapping. This is like an hour already. You guys are gonna hate me again. I might separate the two videos. I don't know. But anyway, that's it. This is the bonus part, factors of polynomials using x-intercepts. Bye, bye, bye. I don't know what I'm doing here.